This is section 6.4 on work. So if an object moves along a straight line with position function s of t, then the force F on the object is given by Newton's second law of motion, which is basically F equals ma, where a is acceleration. So that would be mass times acceleration, which is the second derivative. The units are going to be newtons, which is kilograms, which is the units for mass, and meters per second squared, which is the units for acceleration. In the case of constant acceleration, the force F is also constant, and it's given by this formula, which is work is equal to the force times the distance that you're moving the object. And the units for that, that's called the joule, Joule, and that's equal to a Newton times meters for distance. All right, so let's take a look at this first example. How much work is done when a hoist lifts a 200-kilogram rock to a height of 3 meters? All right, so first we're going to need to, ultimately we want to know how much work is done, but in order to know how much work, we need to know what the force is. We already know the distance, which is 3 meters. The force is F equals m times a, but the acceleration is just the acceleration due to gravity, which is g. So you can call a g in this situation because acceleration is the acceleration due to gravity. And we know that to be 9.8 meters per second squared. So that's something that you want to memorize. And so now you can use that. So the force is going to equal to the mass, which is 200 kilograms, times 9.8 meters per second squared. And that is going to equal 1960 newtons. All right, and now we can use that to plug into our work formula. So that's going to be 1960 newtons times 3 meters, because that's how far we're moving the object, 3 meters, or that's how high we're moving it. And if you compute that, you will get work is equal to 5,880 joules. And that does it. All right, let's take a look at the next example. So this is only for when force is constant. So that's the key, when force is constant. If it's not constant, then you have to resort to this formula here, which is it's a limit of the Riemann sum, which is a definite integral. So its work is going to equal to the integral of the force function times dx. So let's look at this example. When a particle is located at a distance x meters from the origin, a force of cosine newtons acts on it. How much work is done in moving the particle from 1 to 2? So we can set up our formula. Work is going to equal, the limits are 1 to 2. The force function in this case is given to us as cosine pi x over 3 with respect to x. So this shouldn't be too bad. The antiderivative of cosine is sine. And we also have to be careful with this. The chain rule is going to give us pi over 3 if you were to differentiate this. So we have to make sure that cancels out by multiplying by 3 over pi. This would be the antiderivative of this. And then we're going to evaluate from 1 to 2. And that's going to be 3 over pi, sine of 2/3 pi minus sine of pi over 3. And if you have your unit circles, or if you kind of have these memorized, you'll see that they're both equal to radical 3 over 2 in this case, which makes this 0. So the net work is going to be 0 joules. So that just means that there was some kinetic energy that was positive, and then maybe some kinetic energy that was negative, and the net work total, or the net work done, was 0 because it canceled the positive and the negative amount of work. All right, and there is this other law, it's called Hooke's law, that deals with springs. So it states that the force required to maintain a spring stretched or compressed, I should note, I'm just going to write that here, or compressed, x units beyond its natural length is proportional to x. That is, the force of the spring is equal to k times x, where k is just the constant, a spring constant. So let's see how we can apply this. A spring has a natural length of 40. That's important. So in its normal state, this is where it extends to 40 centimeters. There's a 60 Newton force that is required to keep the spring compressed 10 centimeters. So the other thing you need to be careful is the units. This should be in meters in order to be compatible with newtons, because newtons is kilograms times meters per second squared. So we need to make sure that this is in meters. So that would be equal to 0.1 meters. So 10 centimeters is equal to 0.1 meter. How much work is done during this compression? Okay, so remember, we need to find out what K is first. So we know that there's 60 newtons, so that's your force. The K is unknown. And X, we know X is the distance that the spring is compressed, which is 0.1 meters. So if we solve, we're going to divide by 0.1. And we're going to get our spring constant to equal to 600. So now we can plug it back into our force function. And so f of x is going to equal to 600x. And now we can apply the work formula, which is the integral from, in this case, we're going from 0 to 0.1. That's the distance that we're compressing the spring. And we know our force function is 600x with respect to x. And this is it. So if you find the antiderivative, that's going to be 300x squared from 0 to 0.1. And if you plug that in, you should get 3 joules. And that is the amount of work required to compress a spring 10 centimeters. There's a follow-up question. How much work is required to compress a spring to a length of 25 centimeters? So now we're compressing it even more. So it should be more than 3 joules. So let's see, from 40 to 25, what is that? That's going to be 15 centimeters, which is equal to 0.15 meters. So now we're compressing the spring 0.15 meters. So it's going to be the same exact formula. The only difference is the unit. The upper limit is 0.15 now instead of 0.1. And everything else should be the same. So this is going to be 300x squared from 0 to 0.15. And if you plug that in and compute that, that's going to be higher than the previous problem, which is what we were expecting, 6.75 joules. And that does it.